You know, your heart speaks its own language. It's this incredibly precise electrical code that dictates every single beat of your life. Today, we're going to crack that code. We'll look at what happens when the signals get crossed, when the whole system crashes, and what it actually takes to bring it back online. Let's decode cardiac arrest. Think about that for a second. Every single one of those 100,000 daily beats is fired off by a tiny electrical spark. It's this perfectly coordinated dance. But what happens when that electrical code gets corrupted? And this, right here, is the absolute golden rule of the heart. A wave of electricity has to sweep across the muscle cells before they can squeeze. It's the command that basically yells, "Contract now!" So what happens when that perfect signal goes haywire? You know, when there's a short circuit, a traffic jam, or just a total system failure? Okay, let's dive into the algorithms of cardiac arrest and find out. Okay, so before we can really get into the chaos of a system crash, we've got to appreciate just how elegant a healthy heartbeat is. Seriously, think of it like a perfectly designed transit system. Our journey kicks off right here at what's called the sinoatrial or SA node. This is the heart's grand central station. It's where the master clock, the station master, sends out that very first signal to get the beat started. Next up, that electrical signal zips down to the AV node, which acts like a physiological toll booth. And this tiny pause, it is absolutely critical. It makes sure the top chambers have just enough time to push all the blood into the powerful lower chambers before they contract. It's all about perfect timing. After that quick pause at the toll booth, the signal hits the superhighway, this whole network of high-speed fibers. This is what makes sure the big pumping chambers, the ventricles, contract in a powerful, coordinated way, launching blood to your brain, your lungs, and everywhere else. And the amazing thing is, we can watch this entire electrical journey on an ECG. That first little bump, the P wave, that's the commuters rushing into the station. The big QRS spike, well, that's the main train leaving the station, a huge surge of power. And the T wave is just the system resetting for the next departure. It's the heart's whole story in one elegant line. So that's the system when everything's running smoothly. But what happens when the timing starts to fail? Let's take a look at the dangerous traffic jams that can happen on this electrical highway. Now, to really get these delays, or heart blocks, there's this unforgettable analogy about a relationship. So think of the P wave as the plan and the QRS as the response. In a first-degree block, the signal always gets through. It's just consistently late. Every single time. Annoying, for sure, but stable. Now the relationship is getting strained. The delay gets longer and longer until finally a signal is dropped completely. The connection is failing. The communication is starting to break down. Okay, this is where things get way more concerning. The signals are now just being dropped randomly with no warning at all. This isn't just a tired connection, it points to a broken wire somewhere in the system, and that is a much more serious problem that could suddenly lead to a complete shutdown. And finally, the divorce, a complete communication breakdown. The top chambers and the bottom chambers are now just operating on their own schedules, totally out of sync. This is a total electrical failure, and it needs immediate intervention, usually a pacemaker, to restore some order. All right, so we've covered what happens when things are too slow. But what about the flip side? What happens when a short circuit, maybe from a heart attack or an electrolyte problem, sends the heart into a dangerously fast rhythm? The two usual suspects here are atrial fibrillation, which is basically total electrical anarchy, like a chaotic crowd all shouting at once, and atrial flutter, which is actually organized and regular, but it's relentlessly fast, kind of like a marching band that's stuck on a loop. Now, for some of these dangerously fast regular rhythms, there's a pretty remarkable medical intervention. It's a drug that acts like a chemical Control-Alt-Delete for the heart. And this is where it gets absolutely wild. When this drug, adenosine, is pushed really fast into a vein, it temporarily just stops the heart's electrical conduction. For about 6 to 10 terrifying seconds, the monitor goes completely flat, a flat line. But that pause, as terrifying as it looks, is exactly the goal. It's just long enough to break that faulty electrical loop, to reboot the entire system. And in that silence, the heart's natural pacemaker, our grand central station, gets a chance to take back control and restore a normal rhythm. It's incredible. But what happens when the short circuit isn't just in the upper chambers, but in the main pumps themselves? Well, that is the ultimate system crash, cardiac arrest. When a person's in cardiac arrest, emergency responders have to make a split-second critical decision. And it all boils down to one simple question. Is there electrical chaos that we can shock? Or is there just silence? If the answer is yes, if the ventricles are just quivering chaotically, the number one priority is a massive electrical shock. The defibrillator acts like a hard reboot on a crashed computer, trying to just wipe the slate clean and let a normal rhythm come back. But if the heart is electrically silent, a flat line, a shock is totally useless. You can't reset a system that's already turned off. So here, the focus shifts completely to high-quality CPR to manually pump blood to the brain and powerful drugs like epinephrine to try and jolt the system back to life. But, and this is so important, getting a pulse back, restarting that engine, that is only the beginning of the battle. The modern approach to cardiac arrest looks way beyond just the heart. Because you see, the heart can be restarted, but the brain is incredibly fragile. Every single second without oxygen is critical. So the true goal of resuscitation isn't just restarting a heart, it's saving a person, which leaves us with the ultimate question. How do we make sure that when we save a life, we also save the person inside?